Okay, good morning, everyone. And today is Wednesday of Galaxy Evolution Week, and we have 4 tutorials today. We have a full schedule, so I am going to try to make this introduction brief. New image from David Rupke. Keep on populating the beauty channel, Halo 21 Beauty Slack channel, and I'll select something simulation oriented for tomorrow's image. So we will rush through that, and I will just note trivia time. Trivia round, socializing time will be tomorrow at 4:30 p.m. And I'll talk more about that, and we'll have a link tomorrow. So today, I'm happy to introduce 4 people who have volunteered and been asked, actually, to give tutorials, and we are going to have a busy schedule. So I want to have people remember that all of these are going to be recorded. And so if you miss one, if you're in a breakout room afterwards, if you go to another tutorial to join Annalisa or John or Chris or Fari, you can always come back and see the recordings of these tutorials. So each tutorial is going to be 20 minutes of presentation and then 5 minutes of questions, and then I'm going to push you off to the tutorial room, and then we'll move on to the next one. We'll have a break approximately between like 8:55 and 9 o'clock. So, Annalisa, are you ready?
Yes.
Okay, I am going to stop my share, and I'm going to turn it over to you.
So, hi everyone. Today, yes, we're going to talk about the effects of the environment on satellites, as the images at the bottom of the slides are meant to evoke. These are jellyfish galaxies from the TNG50 simulation. But this is going to be a tutorial about effects of halo environment. So we're going to focus on satellites as they fly, fall, orbit in high density environments, as the ones that we typically find within, say, the virial radius of halos, of groups and clusters. So what I have in mind is to propose a mental scheme, a framework to tackle the following fact. All components of the galactic ecosystems, the stellar component, ISM, CGM, dark matter halo, the halo of the host, supermassive black holes of the host, are all interconnected. We're going to do this from the perspective of satellites only for today. And so with this mental framework, we're going to discuss what effects we are even talking about, what mechanisms have been considered as possible causes for such effects with some physical dependencies. But I want to highlight how the hierarchical growth of structure complicates a lot our interpretation. And finally, I want to close with the fleshing out results, a result which we call the directionality of quenching. You will see from time to time things to keep in mind as a note. So the idea of halo environment is pretty clear when we say look at groups or clusters of galaxies in stellar light or stellar mass, like in this image here. There is a beautiful galaxy at the center of the potential well, at the minimum. Usually it's the most massive or most luminous, and it's surrounded by a smattering or thousands of satellites, which are what we are thinking about. Stellar dynamics is actually dominated by the potential, which is dominated by dark matter and gas. So we have dark matter, gas, and stars. And so this immediately suggests us that when we think about satellite-host interactions, we should group them in 3 categories: gravitational, hydrodynamical, and let's call it radiative. So gravitational, let's say interaction with the host potential, like tidal stripping, or with other galaxies, say tidal shocking. Hydrodynamical with the host intra-halo gas, like ground pressure stripping or other galaxies. And I put under head of radiative anything that I think could, in principle, affect galaxy satellites evolution, say because they are in a given ambient radiation, or they can be affected by directional sources of radiation, say from the central AGN, from the central AGN at the center of the host. Or maybe their evolution is affected via cooling because of the enrichment of the ambient gas. And so for this audience, we're really more thinking about the hydrodynamical and maybe radiative interactions. And it's all about the properties of the intra-halo gas, not just gas density, but also gas temperature, or gas metallicity, And also satellite evolution may depend on how this intra-halo gas is homogeneous or heterogeneous, and how it moves, how chaotic or turbulent it is, as you can see here in velocity field or even in energy dissipated through shocks. Now, when we think about the effects of the environment, what are we thinking about? Let's talk about a couple of observational facts. Observed facts, both in observations or both in the sky, and more recently also realized in simulations. So we're thinking about properties of galaxies like stellar morphology, stellar formation activity, and gas content, but also possibly stellar sizes, gas metallicities, X-ray luminosity of their halos, AGN activity, stellar to halo mass relation. In a nutshell, and I'm gonna really flash the result, is satellite galaxies in groups and clusters have been observed to exhibit, on average, lower star formation rates, redder color, higher quench fractions, lower H1 gas content, elevated gas metallicity, reduced X-ray, halo emissions, suppressed, on average, AGN activity, higher stellar to halo mass relation, in comparison to similarly massive analogs in the field. So this was very fast. This is all the state of the field. We're gonna focus on the three more important things: morphology, star formation activity, and gas content. Thinking about stellar morphology, it's an observational fact that the fraction of spheroidal-like galaxies is higher in high-density environment. This is the famous Dressler relation or morphology density relation. If you count how many, the relative fraction of elliptical or S0 galaxies is higher in higher density environment than in low density environment, say if you measure how crowded they are based on galaxies or how close you are to a central cluster, and they're higher than spiral. Low mass galaxies are typically star forming. So you can see this when you plot quench fraction versus stellar mass. The different panels are different redshifts. You can see both observational data in gray, say here it's from Cosmos and Candle, and from simulations like TNG and Illustris. What I want you to notice is that below 10 to the 10 solar masses, galaxies are mostly star forming, and above 10 to the 11 solar masses, galaxies are mostly quenched. And this is true both in observations and already at redshift 1.5 or so. And it's also true in simulations recently. However, this is true when we look at galaxies combining satellites and central. So the statement, low mass galaxies are typically star forming, it is true unless they are satellites. And so if you take a quench fraction plot and you divide it in centrals and satellites, you actually see that the quench fraction of low mass galaxies is much higher for satellites than centrals. This is again SDSS data in gray, some simulations, and TNG 300 in black. All right. And we are looking at satellites as galaxies which are orbiting within, say, 10 to the 12 to 10 to the 15.2 solar mass halos. Final observational fact that I want you to all be aware of: satellite galaxies exhibit lower H1 fractions than their field counterparts. You can see it here: H1 mass over stellar mass in log as a function of satellite stellar mass. Data points are observational results from X gas on the top, alpha alpha on the bottom, and curves are from TNG. Centrals are in reddish, pinky, and satellites are in cyan. And you can see that centrals have higher gas fractions. This depends, of course, on where you're looking at. This is why it's different between X gas and alpha alpha, the beam size, for example. In TNG, this is happening while our galaxies are beautifully around pressure stripped, as you can see on the left in H1 map of a group of galaxies. So what's going on? I think it's useful to simplify a little bit the perspective. And I would argue that it's not a simplification. I would argue that it is all a matter of what happens to the gas and to the gas availability. So this is actually generally true to up to second order, I would say, in galaxy evolution. But it's also true in this context. So if you think about star formation activity and gas content, of course, they're obviously connected, modulo, say, cooling and the availability of gas in specific gas phases. But also when you think about morphological transformations are strictly connected to availability of gas, because you cannot have a persistent morphological change unless you avoid new star formation, because new star formation will replenish a stellar disk. And so, you know, reversing again any morphological transformation that you might have had by just, you know, kicking the stars and changing their orbits. And so let's focus on the gas content and gas availability. And instead of talking about the buzzword that you often hear in environmental studies, I just ask us, what can happen to the gas of satellites, both the ISM and the CGM? Can be consumed or depleted, can be heated up or cooled down. It can be ejected, it can be compressed. Its replenishment can be suppressed, or it can be removed, stolen, okay? So the first four happens in centrals or field galaxies. I use centrals and fields as synonymous. And they are due to a zero order to internal processes. But for example, the suppression of replenishment of gas or fuel of gas is typical of satellites, and the removal is also just typical of satellites. So, for example, gas can be depleted via star formation. It can be heated up or ejected via internal feedback, supernova, supermassive black holes, or even can be compressed or funneled into the center of galaxy via galaxy-galaxy mergers, which I would say they are different than the host environment interaction we are talking about. For satellites, the replenishment of gas can be suppressed in the sense that it can be stopped. The gas accretion, cosmological or from the surrounding, can be stopped just because they are flying in the potential well of a more massive guy. And gas can be removed via tidal stripping, via run pressure stripping, or via repeated encounters with other satellites. So thinking about these famous buzzwords, people have called harassment these repeated encounters with other galaxies. They're called the combination of depletion via star formation and lack of replenishment. They have called them starvation or strangulation. The point is that with satellites, we have so much more complications because, for example, you can heat up and eject the gas of satellites because of the interaction with the effects of feedback, not from the satellites, but say from the central of the host in which you are orbiting in. And run pressure stripping can remove gas, but can also compress it at the same time. And so, as you can see, all of those happen at the same time and simultaneously. Sometimes at the same time, in the sense that we can even see star simulation, star formation happens at the same time as stripping of both stars and gas. And the effects can combine together, sometimes constructively or not. For example, if you heat up the gas via supernova feedback, you may make it less gravitationally bound, and then it's easier to remove it, say, via stripping, tidal or run pressure. And so then the question becomes, okay, which phenomena are most relevant? And it depends on what effects you are looking at. I would argue that the physical regime where certain physical mechanisms, say like run pressure stripping, are strongest, are not necessarily exactly the same as the physical regime where the effects on galaxy properties are the largest. Because this is all complicated by the hierarchical growth of structure. We come to this in a second. But I would say, let's focus on the physical regimes where the effects on galaxy properties are largest. Or let's try to find some causality. So for example, in TNG, the lower H1 gas fraction are easily explainable by run pressure stripping. So we have run pressure stripping properly captured in the simulations, and they produce jellyfish galaxies. Jellyfish galaxies are observed, they are beautiful, and you can see them with these tails. So this is another way of looking at jellyfish galaxies from TNG. Some look like tablecloth, where the gas is stripped from the side of the table. Others look like very elongated small streams of gas. We can go in the simulation and actually look at what is the fraction of jellyfish galaxy among satellites. We can do it visually inspecting the simulations, and we can say, for example, that the lower the satellite mass, or the larger the host mass, the larger is the fraction of jellyfish. But we don't see effects on redshift. Let's think about the dependencies of quench fractions. The quench fraction of satellites depend on host and satellite properties, but also on the evolutionary state. This is a summary that both observation and simulations agree upon. For low mass galaxies, lower satellite mass implies higher quench fractions. Higher host mass implies higher quench fractions. Higher redshift, lower quench fraction if you fix everything else. At fixed satellite mass, for low mass galaxies, lower cluster-centric distance means larger quench fractions, but longer time since info also imply larger quench fractions. As I said, though these are quantitatively supported both by observations like SDSS data in these plots here, or simulations like TNG, again, here in curves. I don't want you to look at the plots. I mean, these are too many, but I'll leave them in the slides. But what I want to focus is maybe as these dependencies, and some of them are clearly very well compatible with the dependencies of run pressure. Run pressure is larger, the larger is the medium density, and goes like V squared, where V is the relative velocity between the gas and the satellite, and the gas which the satellite is hitting upon. And so you can imagine that larger host mass imply higher ambient density, and therefore higher run pressure. Higher host masses imply a higher satellite orbital velocity, and therefore higher run pressure. And lower cluster-centric distances imply higher ambient densities and higher run pressure. So these are, of course, very useful, but they're not the whole story. Because what we see at a certain point, and we can think about the physical mechanism acting at a certain point, actually is the result of billion years of complex evolution. Let me remind you how complex is the hierarchical growth of structure. This is the assembly of a group of clusters, 10 to the 14, is two gigantic groups that are going to merge together with smaller groups, which are merging with the bigger one. And the satellites are orbiting in both these groups and in the final host. So I want to talk quickly about three facts: pre-processing, phase space, and backsplashes. So pre-processing is this idea that when we look at satellites in a given host, say at ratio 0, these might have fallen as centrals, or they might have fallen as satellites of other group, and together with their little group have fallen into the final host. So pre-processing depends on stellar mass of the satellites and host mass where you're looking at it. So we can use the simulations, and I can tell you, for example, that according to TNG, more than 50% of 10 to the 9, 10 to the 10 solar mass galaxy, which we find today in groups of 10 to the 14, have been satellites of other massive hosts before falling into their final hosts. So these are a number of effects, right? Firstly, preprocessed galaxy may have endured galaxy host interaction for a very long time, but they might have fallen into their current host already affected, already quenched, already spheroidal, already devoid of gas. So we can measure all this in the simulations, and whenever we look at galaxies, even in the observation, which are quenched satellites at ratio 0, we can ask, did they quench the satellites, or did they quench the centrals? And if they quench the satellites, did they quench while they were orbiting in this host, where we find them today, or in another host, which then fell into the host where we found them today? And if they quench the satellites in their current host, have they been pre-massaged by some other interactions before? And so this gives us a thing to think about. Yes, more massive hosts are more efficient at affecting satellites. This is true in general: quench fraction, gas fraction, morphological changes. But this is a concurrence of two reasons. The physical mechanism that may be responsible for this may be stronger in higher density environments, but also the more massive halos hosts are the ultimate product of the hierarchical growth of structure. And so they have many more, the higher fraction of their satellites have been pre-processed. Another thing that I want to point out is this idea of the phase space. We touched upon it when talking about the Milky Way and Andromeda. So satellites that fell into their current host a longer time ago are typically found closer to their host center. This is radial velocity versus cluster-centric distance, and the red satellites are galaxies that fell into this the cluster we're looking at billion years ago. And so this has an impact that the effects of environment depends on where satellites are located at the time of observation. We could even translate this by looking at the star formation histories of dwarf galaxies, and we see obvious trends of these star formation histories on the right in TNG, depending on where we find the satellites, whether we find them very close to the centers or not. And then again, this gives us something to think about. Satellites closer to the host centers, yes, are more affected by the environment, but this is it's because maybe two reasons. Physical mechanisms like ground pressure stripping may be stronger in higher density environments, and therefore closer to the host center. And satellites orbiting closer to the centers have typically spent a longer time, and so they have longer aeons, billions of years of host-galaxy interaction. And finally, there's plenty of backsplash galaxies in the world, but those we mean galaxies that appear central and in the field, but actually have been in the past satellites of nearby, but not too close by, groups and clusters. We call them backsplash. The complication is that, I skipped that. The complication is that they contaminate our samples and our understanding of centrals and field galaxies. And so if we were able in the world to even remove from observed galaxies the ones that have been affected by some prior satellite membership, so removing the backsplash, we would even get, lower quench fractions, but it depends. All right. So this was all about, I wanted to say, when thinking about the environment, very complex. And I want to close with flashing a result, if I have a few minutes still. Yeah?
You have about, you've gone on for 19 minutes, so you have 25 minutes. So go on for a couple more minutes, and then we'll move you to the breakout room.
Okay. I want to flash a result that is really putting together many of the things we have talked to you about. And I find it as the quintessential manifestation of the connection between the CGM properties and the effects it can have on satellite galaxy properties. And so we have queried SDSS data in relation to the quenching of satellites. And we have found that the fraction of quenched satellites depend on their location with respect to their central galaxy. So here is your typical halo, Darmstadt halo, hot gaseous halo. Suppose you have a central galaxy. You can always define a photometrical minor and major axis, even if it's an elliptical. And then you have galaxies in different locations. So you have galaxies, say, along the minor axis of the center, or along the major axis, the major plane of the center. And so we have found a dependence on whether satellites are where they are with respect to the plane of the central. And so I don't know whether we managed just to do it now live, but I would like you to at least think about, or go to menti.com and maybe just really
Yes, I can share the code in the chat. Just a moment here.
Yeah.
I know the answer.
And so I want you to try to say, so which satellites are, so the starting point is that satellites are very much quenched, okay, at low masses. And so what satellites are relatively less quenched, according to you? The one that are found along the minor axis of the central, or the ones that are found along the major axis of the center? I hope the question is clear. And I don't know, we can have a few seconds to think about it. I don't know whether people are voting or not.
People are voting. The votes are pouring in.
I'm really curious about this because Annalisa gave a colloquium here at CU, and the results were different. I think the results will be different here.
I see, cool.
Experts.
Okay.
Really excited.
Jess, do we want to say the winner according to the audience?
Well, so only 20. Okay, the votes are still pouring in. The numbers are going up rapidly, so maybe give people another full minute to kind of contemplate what they think their answer should be.
And we'll have Chris get ready. He's going to start in about 3 or 4 minutes. And you can see the breakout rooms. Annalisa has one.
Mm-hmm. So I think I will give you the answer.
Okay. Okay. So this is so with 35 people having voted, 56% say minor axis. Oh, it just changed. 57% say minor axis. 58% say minor axis.
Very good.
39% say major axis.
Very good. Sorry, I went away. Very good, guys. The answer is indeed 1, is along the minor axis. So we have an audience of super experts. So what we think is happening is the following. So in SDSS, satellite quench fraction are lower along the minor axis of their centrals. You can really see it here, quench fraction as function of orientation. The minor axis is here, and it's a small phenomenon of a few %, but it's statistically significant. Also, we see that this anisotropic modulation in SDSS is stronger for satellites closer to the center, for lower mass satellites, for halos with more massive centrals, and for halos host with relatively more massive supermassive black holes. And we have the same in TNG. Also in TNG, we have an anisotropic modulation for which the quench fraction of satellites is a little lower along the minor axis of their central. And so in TNG, we could go and ask, is this a manifestation of a large scale phenomenon or a whole stellar phenomenon? And we really think it's a whole stellar phenomenon because we don't find the same modulation in Illustris, which has the same large scale structure of TNG, but different feedback. The modulation in TNG is stronger around quiescent galaxies and around centrons with more massive and more energetic supermassive black holes. And the modulation is certainly driven by galaxies which quench in the redshift zero host. So what's happening? We think this is a manifestation of supermassive black hole feedback from the centrals. As a reminder of what Dylan told you, at least in TNG, supermassive black hole feedback ejects and hits the gas within and around galaxies. And the outflows and the effects are coming out in a bipolar manner, even if the feedback injection is isotropic. In practice, what happens is that supermassive black hole feedback from the central galaxy, at least in TNG, carves lower density region in the circumgalactic medium around the centrals, and particularly so along the minor axis. So if we then plot the gas over density as a function of orientation by stacking many halos, we still see a difference. And I think that this lower density affects the possibility of quenching galaxies. Lower ambient density means lower run pressure stripping of satellites, less gas removal, lower quench fractions. I thought that I had to show you this because it's incredibly cool. And maybe the interpretation is wrong, but this really is a manifestation of the interaction between the supermassive black holes at the center affecting the CGM, which in turn affect the, if we understand it correctly, affects the evolution of satellite galaxies.
Excellent point to finish the main session on, and I will have those interested go into the breakout room. I know there's some satellite experts here.